Good morning and welcome to the Thermal Transport Cafe. For those of you who don't know me, my name is 𝗕𝗏. I'm an assistant professor in mechanical engineering at the University of Utah. Today's speaker is Dr. Duarte. She is an assistant professor in the engineering physics department at the University of Wisconsin-Madison, working on safety analysis of nuclear reactors. Prior to joining UW-Madison, Professor Duarte was an assistant professor of the nuclear and mechanical engineering programs at Virginia Tech. Her research interest is in experimental and computational two-phase flow and heat transfer, reactor safety and risk analysis, and advanced reactor designs. The title of her talk is Density Wave Oscillations and Dryout Rewet Cycles in Boiling Water Reactors. With that, Juliana, the stage is yours.
Thank you for the introduction. So this is the title of my talk today, and this is the outline. I'm going to give a brief introduction on two-phase flow instabilities, the motivation of this work. I'm going to talk about the experimental data that we have been using to study the density wave oscillations, which is one kind of two-phase flow instabilities that can occur in boiling water reactors, and discuss the analysis results and current conclusions that we have about this work. Before I start, I just wanted to acknowledge that this is part of an ongoing project that involves Virginia Tech, UW-Madison, and the University of Louisiana-Urbana-Champaign. These are the results of the first 2 years of this work, and a lot of the work was done by the PhD student 𝗕𝗏𝗪 that it's shown here. He just graduated last month. So to start with, two-phase flow instabilities can occur in several problems that we study on the interface of two-phase flow and also on the systems that has boiling occurring. They can be static instabilities or dynamic instabilities, and the most common dynamic instabilities that we can observe is called pressure drop instabilities or density wave instabilities. The difference between them, it is the frequency and also where these instabilities occur in this pressure drop mass flow rate curve. If you look to the curve on the right side, the left side of this curve, if you can see my pointer here or the mouse, shows the single phase pressure drop, where the mass flow rate increasing, the pressure drop will also going to increase. And this is for a constant power that we are applying to your flow channel. As we start boiling in the middle point here, and you're starting creating two-phase flow, as the mass flow rate now decreases, your pressure drop is going to actually increase for lower void fraction regimes. So in these situations, when we have this negative slope of the pressure drop with the mass flow rate, we can observe pressure drop oscillations, which they are characterized by lower frequencies. If we are operating our channel in higher void fractions, and we can observe density wave oscillations that are characterized by high frequency oscillations, and they occur due to the formation of the void fraction in the channel that are going to cause a delay in the response to the pressure drop and a feedback in the system, leading to instability regimes that in the case of nuclear reactors, it can lead to a more severe accident. So this is just a brief introduction on dynamic instabilities. The density wave oscillations, which is the kind of instability that we're interested in, they occur, as I said, because of the shifting phase between the inlet mass flow in the channel, which should be usually still single phase flow, and the total pressure drop in the entire channel, the entire boiling length, not only the boiling length, entire channel, including the single phase and the two-phase flow lengths. Once these inlet mass flow, it is completely out of shape with the total pressure drop, these instability or these oscillations, they grow because it has kind of a negative effect on the friction coefficient that leads to the increase of the mass flow rate. In the bottom left curve here, it is a theoretical explanation of this density wave when you have the inlet mass flow on the bottom here, and you see the pressure drop getting out of phase until the total channel pressure drop, which is also with phase of the outlet pressure drop, showing that the formation of vapor in the channel, you cause these two components of the mass flow rate and the pressure drop in this channel to be completely out of shape at some point. And when you look to the experimental data, that condition, it is the condition that leads to the growth of this oscillation. So I'm going to talk more about the experimental data later, but just for you to visualize what's happened, in the data that we are analyzing, we have the power here in green increasing by the operators of the experimental facility over time. And we have the mass flow rate increasing at some point when we have this shift, completely out of phase shift between the mass flow and the total channel pressure drop. And at some point, these larger amplitudes at this oscillation can lead to critical flux and rewet cycles, and eventually to a failure to rewet, which is characterized by the increase of temperature that cannot be recovered anymore, and then it can lead to a damage of the few rods and potentially a meltdown of the rods. The motivation of this work. So this data was collected back in 2016 and 17. And the main motivation that NRC commissioned this data back then was was boiling water reactor instability during anticipate transients without scram, or ATWS. Specifically for reactors that were applying for MELLLA plus boundary condition. What that means? It means the boiling water reactors, they have been licensed for certain power and certain mass flow rate for them to operate. A few years ago, several of them applying for extended power operate, where they allow to operate at 20% of the original license, which you can see here by the MELLLA boundary. And some reactors, at the time that the NRC collect this data, were applying for MELLLA plus boundary condition that you allow them to operate at a higher power but lower mass flow rate, which could give them some flexibility in the operation of the reactor. But what happened when we analyze the accident scenarios in these conditions, the ATWS, when we have the dual recirculation pump trip, that will lead to a natural circulation condition in the reactor core. And you see here in this curve, we could have then an increase of the power at lower mass flow rate, which should be a condition of this density wave instability that could then lead to a more severe accident scenario with damage of the rods. So you're interested in understand more this phenomena and also understand our ability to simulate this phenomena and being able to predict it properly using the NRC codes. So the data was collected at CATI facility in Germany. I said back in 2016 and 17, and there was several sets of data that they collected, and we analyzed it here at Wisconsin, at Virginia Tech, and the University of Illinois. The data was collected at this facility because this facility has the capability of perform boiling water reactor conditions like pressure, mass flow, and temperature, but also has the ability to, in a full-scale 10 by 10 boiling water reactor, a rod bundle, but also has the facility to conduct natural circulation experiments, and also to have a kind of a neutronic simulator that they call CINA that provides the power of the electric heater rods a kind of feedback that you change the power during the experiments to simulate the void fraction feedback. For those that are not nuclear engineering, is basically if you have less liquid water in the core, you are moderating the neutrons loss, which is what we need in order to cause the fission in this kind of thermal reactors. And I said, if you have more water liquid, you're moderating more, actually. And if you have less liquid water, you're moderating more. So the water liquid moderates these neutrons to become thermal neutrons and then cause the fissions in those reactors. So there is a feedback mechanism between the void that you have in your channel, the void fraction that you have in your channel, and the power of your channel. So the experiments that was done in this facility was first single phase and two phase pressure drop. So we could characterize all the pressure drop of the grid spacers and the pressure drops in the channel and in the whole test section. We done the steady state CHF, so we could predict and identify which would be the best correlation to predict critical flux at this facility. And then they perform this natural circulation, dryout, and rewetting cycle experiments with and without the void fraction feedback mechanism. At the top of this slide, you can see the rod bundle that was used in this experiment is a 10 by 10 rod bundle with water channel. The P represented partial length rods, and the numbers represents the power peaking in the bundle. So number 1 are the rods with highest power, and number 4 are the rods with lower power. And also we had a power profile that was 𝗕ance shape that represents a boiling water reactor as well. But the actual power profile is proprietary, so we cannot show it. But it was not uniform. We actually had an actual power profile in all of these rods representing a typical boiling water reactor. We perform the characterization of the pressure drops and the steady state CHF before this research award has actually started. And I'm going to be talking more today about the natural circulation density wave oscillation data. How do the data looks like? For the experiments that were conducted without the void fraction feedback mechanism, which is the seen and cold, basically they achieved natural circulation in the facility, and they were increasing the power by steps. You can see in the top figure, in observe the mass flow rates. The mass flow rate. So the mass flow rate at some point in the last power increase became from a small oscillation that is still like a stable condition becomes an unstable condition and grow. The actual end of these experiments was led by the fail to rewet event, which you can observe in the bottom plot, because at some point, these are two different experimental data. They have the similar behavior, but the bottom one, you can see each of these phase for a longer period of time. So we have the onset of this density wave oscillations, or DWOs, at the first part here in about 50 seconds. And then the power was increased again. And then we started observing dry out and rewet cycles. And now in the blue here, you're basically seeing one or more thermocouple that start experiments the temperature increase, that it's from 30 or 50 Celsius degrees. So it is a dry out condition. But because the mass flow rate is oscillating, this temperature goes, these thermocouples measure the temperature increasing because of dry out, but also measure the temperature decreasing due to the rewetting of the walls. If this is going to continue to happen, at some point, we're going to observe the fail to rewet, or FTR, which is the point where even with the mass flow rate increasing, the broad surface, it is not rewetted anymore. And then at this point, the experiment was terminated by decreasing the power and recording the data. And just to highlight here, the conditions that these experiments were run were 7 and 8 megapascal with inlet subequivalence of, this represents, I believe, 40 and 20 Celsius degrees subequivalent, 193 joules per kilogram, and natural circulation. This is just a highlight what it means by the fail to rewet. You can see the dry out and rewets occurring before the event, and at some point, one or more thermocouple experience this temperature increase that it's much higher than the other oscillations. And even with the mass flow rate going up here in about 420 seconds, the temperature of the rod, it still keeps going on. Then the power, it is decreasing at this point and the data is recorded. For the data that had the void fraction feedback, they were performed a little bit different. So in this case, there was the Sinan model that was controlling the power of the bundle. However, the way that they performed the experiment, it is keeping the actually average power of the bundle constant and allowing it to increase and decrease by a neutronic feedback that is proprietary as well. So we are not fully simulated exactly the experiment, but I will tell you later what we did to compare some simulations with this data. What they actually did was to, for each experiment, they fixed the field thermal inertia that also simulate the time delay between the void fraction and the power change to match a boiling water reactor. So they fixed the field thermal inertia, and they fixed the higher mode harmonics in the neutronics part. We could know what it is, but as I said, the actual code is proprietary. And then they change the void reactivity coefficient during the experiment. So this VRC-MUL variable, it is the void reactivity multiplier. It's actually multiplied by the void reactivity coefficient that allows to change the power. So as the mass flow rate oscillates, the experiment facility predicts a void fraction. This void fraction changes the rod power of the bundle and allows to oscillate around an average power. And this happens again until we observe large oscillations that lead to the fail to rewet phenomenon that I just showed you. So after, for the thermocouples, we'll be observing the same phenomenon. The first thing that we did to analyze this data, it was to understand what was the main variable that was driving this failure to rewet. So the first thing was to look for this mass flow heat transfer coefficient, the maximum temperature before we had the failure to rewet, and the failure to rewet itself. So this is a busy plot, but if you look here, we have in this gray and orange here, this is basically the temperature of the rod. The thermocouple was on the inner side of the rod, and the rod was electrical heater. So we did a 2D inverse heat transfer to calculate the surface of the rod temperature. So this is the difference between the orange and the gray. It is the inner and inner and outer surface temperature of the cladding that was being heated during the experiment. And we tried to understand what is the difference between this maximum temperature that water is still able to re-wet and the temperature where we're not able to re-wet anymore. So we had to shift the mass flow rate for the local mass flow rate at the location, the height location of the thermocouple. So you can see the mass flow rate here in blue. And also we calculate the heat transfer coefficient of the wall to the two-phase flow mixture. And we see here when we have the fail to re-wet at about 418 seconds, that the heat transfer coefficient gets like stuck into the fume boiling regime. And even with the increase of the mass flow rate, that temperature, it is much higher than our minimum fume boiling temperature. And that increase in the mass flow rate, it is not enough to re-wet the surface. So this was kind of preliminary analysis that we did to compare with the models that we have in TRACE. So TRACE, it is the thermohydraulic code that NRC develops to simulate mostly light water reactors. So we are simulating the momentum, mass, and energy equations for the liquid and vapor phase. And TRACE code has the capability to simulate also the controllers and all of the devices that we have in a nuclear facility. So valves and pipes and the bundle and everything. So this is a very short summary of what we found, because we compare this maximum temperature before failure to re-wet with several correlations that predicts the minimum fume boiling temperature. And they vary a lot in their predictions, between a few dozens of Celsius degrees to even a few hundreds of Celsius degrees, depends on the correlation that you are using. And to be conservative, we actually have to use the lower boundary of these correlations in order to predict this failure to re-wet. And I put at the conclusion here, which the homogeneous nucleation temperature, which is actually a very low bound of the minimum fume boiling temperature, actually provides this conservative boundary for this phenomena. If we use that, we can say, yes, we're going to be able to predict the failure to re-wet for this data that represents boiling water reactors. All the correlations that predicts this transition between the transition boiling heat transfer to the fume boiling heat transfer, they predict a few degrees or even hundreds of degrees, I said, of minimum fume boiling temperature higher than the homogeneous nucleated temperature, and then they will not be able to predict this phenomena. And this is just a sensitivity analysis for a few temperatures for the minimum fume boiling temperature. And you see here in black is the experimental data, and in orange is the wall surface after the two-phase, after the 2D inverse heat transfer. And when we use the 110 Kelvin, we predict the failure to re-wet a few oscillations before. If you use 620, you're going to predict the failure to re-wet closer to the experiment. But if you're using 30 Kelvin degrees, more, 30 Celsius degrees more, you don't predict that failure to re-wet at all. So you're not being conservative anymore. And these are close numbers, but the correlations uncertainty is even higher than that. And just since we are talking here about two different models, right, we have critical flux and the rewetting that is driven by this minimum fume boiling temperature. I just want to show you this plot here on the right that shows that the critical flux for this facility actually was very well predicted by the Louka paper 1995. which was the available version for the lookup table back when we did this analysis. So there was no change in the critical heat flux model here. We didn't have to do anything except when I was doing the analysis of the local heat transfer, then in order to have the critical heat flux occurring at the same location of the experiment, then we have to play with the critical heat flux multiplier. But if you're only predicting the total power of the bundle that occurs critical heat flux, the lookup table predicts very well with this plus or minus 10%. So this sensitivity analysis here was only to show the minimal film boiling temperature effect on this phenomenon. And the heat transfer analysis, I'm gonna talk a little bit later, but it's still an ongoing analysis of this project. The next thing that we did when we were looking now for the actually onset of these instabilities, we looked for the definition of what it means to have these onset of instabilities. In some experiments, actually, it's very clear. I put an example here that is actually very clear. We have this growth oscillation, and with the mass flow rate, which leads to the power growth as well. And we observe the phase to rewet, and that's it. But this is not very clear in our experiment. Sometimes you can have this very stable mass flow oscillations that are not necessarily characterizing of a density wave oscillation that or the instability that we are looking for. And you look to the literature and the definition of this onset of instability, it is very unclear. Some examples here, an author put a 10% of the mean of the mass flow, another put 5%, and even 100% of the amplitude of the mean of the mass flow rates. So in order to try to have a consistency in our analysis, we propose to have this actually phase shift criteria to define the moment where these oscillations are growing, and then we characterize that as an unstable condition. And we did that, and we can see, and did for all the experiments with and without the neutronic feedback, and we can very clearly see that the moment that the total pressure drop and the inlet mass flow phase shift between them, that is defined here on the left, they grow and they go through this completely out of phase. It is the moment of these oscillations grow in a significant way. And after that, if you don't have critical heat flux, you're just going to have these very large oscillations that could lead to the dryout and rewet cycles. But these phase shift, actually, we found based on this data, it is a very visual mechanism when we're doing the data knowledge to define the onset of instability. So this was our definition for the experimental data. With that in mind, we first compare this onset of the instabilities to some old analytical models before we did the trace simulations, because we also simulate this data with trace so we can understand the ability of trace to actually predict these oscillations and these instabilities. But first went back in the 70s, and there are some very useful models that use drift flux model to predict the onset of density wave oscillations. So we compare mainly with 4 models. 𝗕cie, 𝗕𝗏 and Zuber has a simplified model that I'm going to show in the plot, and 𝗕𝗏 and other authors also have a conservative plot that I also going to show in the plot. But the idea is we have the the drift flux model that we can solve analytically. The boundary conditions are very simplified. There is a constant pressure drop at the exit of our channel. The inlet temperature is constant, and the inlet velocity, now instead of having an average into velocity, we add a perturbation to this velocity. And this perturbation will affect the vapor production, the boiling length, the local pressure drop, and it's going to change the stability of the channel. When you solve the Ďurichlet equation model, we can find this characteristic function, which is basically the pressure drop equals to this perturbation that we add, and everything inside of these brackets are the characteristic functions. And at the moment, this characteristic function is negative. That is the definition of the instability. So it kind of go back to the idea that at some point we have this negative feedback for the friction part that is going to lead to the mass flow rate to grow, and you're going to lead to an unstable condition. There are other models in the literature that are more simplified that we also use it, but it was more to compare some parametric effects of some parameters in this model, which are not gonna be talking about today. But the main difference between Saha and 𝗕ន់, it is that 𝗕ន់simplified his model by ignoring the subcooler boiling. So 𝗕ន់only considered thermal equilibrium in the two phases, so we ignore all the subcooler model, where Saha included a function that I didn't add it here, but it's a function that tries to model the subcoolant boiling by modeling the actual void fraction before our quality is equal to 0. And on the right side, we have our instability plot, or sometimes called Zuber plot, which is the subcoolant number versus the phase change number, which the definitions are shown here. The I is the enthalpy, and the other variables are as the ones that we usually use: the density, power, mass flow rate, etc. So another characteristic of the CAT data, this data that we are analyzing, which is very unique, it is that we are working with very low subcoolant numbers compared to old data, existing data in the literature. So this data is unique because it's a full rod bundle at boiling water reactor conditions, and also at very low subcoolant number, which is a region where these models, you can see they have a larger uncertainty. But even with all the simplifications, doing like a simply drift flux model, you see that the data here in this axis, it is very close to the Saha model. As I mentioned before, the simplified version is basically a line here at the bottom, which actually follows very close to 𝗕ន់model. And the conservative one, it is this, I said the opposite. The simplified, it is the square, and the conservative one, it is this line that actually that's following very well the 𝗕ន់model, at least for these pressures. I'm showing here the 7 megapascal because it's the pressure that we have the most of the data, but the same thing happened for the 8 megapascal condition, which is it is close since we're working to pressures that are close to each other. Still with there's a mistake here. This is still with the density wave oscillations without the neutronic feedback. We created a model in trace, now the NRC thermal hydraulic code, to mimic these experiments conditions and also the procedure in the experiments, and to find the unsettlement stability predicted by traits. So we have a lot of information about the test section. The loop itself, there are parts that are proprietary. So we simulated with our best guess. There are some parts here of our simulation that was done only for the initialization. But basically, you have a natural circulation loop where you allowed the vapor to live here in the steam separator, as is done in the facility. And then we bring back liquid water through a feed water controller to also keep the inlet temperature constant. So this is exactly as was done in the facility in terms of the definition of how these things works. The inlet temperature was kept constant, and they do have a steam separator that shows the public figures, and they have a feed water inlet that adds this liquid water to the down corner back to the system. But as I said, some of the uncertainties that we had to move throughout this last year of the project was to find appropriate pressure drops or K factors throughout the loop, since we don't have data for the loop. All the data that we have is for the test section. We did that, and after finding the most appropriate K factors, and also making all the numerical tests in trace to make sure that any of the oscillations that we are observing are not due to the numerical problems, trace was able to simulate in a very good way the amplitudes and the frequencies of this oscillation. So we see on the left side the amplitude, and you see in the right side the Fourier transform of the oscillations that shows the frequency about 0.4 hertz for most of the data. The one thing that trace does not do well, it is to simulate the shape of these oscillations. You see the blue lines here are trace, which have this wiggle here at the bottom. And the reason that we believe that it's happened is because trace change. This is a snapshot of a time, but we are also having the dryout and rewetting. So trace is changing between pre and post CHF flow regimes, but also the void fraction is changing from dispersed flow to the transition flow in the post CHF. So there are several if functions that are making trace to switch from one model to another in a very short period of time. And this is the reason that we believe that we have this wiggling here at the lower mass flows, when we are switching from flow regimes and also heat transfer regimes that are not necessarily capturing the physics of these transition models. When we compare now the instability boundary that trace predicts with the data, is remarkably good. So trace is not, now we are simulating the liquid and phase conservation equations, and it's not as simplified as the Drifty model. And we were able to capture the boundary here. It is very close to the data instability conditions that we define as with the phase shifty method that I explained earlier. Moving for the third part of our data analysis. Now, in order to analyze the data that actually has neutronic feedback, we cannot do with a full neutronic models because the data was not simulating exactly what happened in the exactly what happens in the reactor. The CNA model, they do simulate a lot of things that happen in the reactor, but when we transform that to the bundle, there are some differences that are large, like very large difference. One of them, it is the shape of the axial power. It is fixed in the experiments, since the shape of the power is given by the thickness of the cladding that have been used in the experiments, while in the actual reactor, the shape of the power is going to change, depends of the void fraction that you have along a channel, and depends of several other reactor physics properties of your field. And another large difference is, during the experiment, they kept the average power of the bundle constant and only allow the oscillations of the power to fluctuate around this average power. So in order to have a direct comparison with the data in a simulation, what we did was to create a control model in trace that included the point kinetic equation to do exactly as it was done in the experiment. So this is the schematic of the point kinetic equation, where we can see the change in the mass flow rate, change the void fraction, we change the pressure drop, and you have a feedback here too. But the void fraction, we're going to change the void reactivity, the reactivity of the core, and then changing the power, which you're going to again change the void fraction, the mass flow rate. So this is a generic schematic of what is happening during the experiment. There is also a possibility to have a manual reactivity change, but we not use that, since they did not use that during the experiment. They will only change the void reactivity coefficient multiplier during these experiments. And then we analyze several things, and I summarize here because of the time. But the first thing we did was to mimic the experiment by increasing this void reactivity multiplier until we have these oscillations and until we have these instabilities growing, and you can observe in the mass flow rates and in the power oscillations here. When you do that for the conditions of the experiment, that includes different field thermal inertia and different different pressure and inlet to the coolant, Trace was able to predict, and you can see on the right side, the experimental void reactivity multiplier that led to the instability versus the predicted void reactivity multiplier in Trace for the same conditions for these few data points that we have here. I didn't add it in these presentations, but we did sensitivity analysis for all of the parameters that we use in the simulations. For the fluid side, we did the sensitivity analysis for the K factors, and we looked to all data for the geometry. And for the neutronic feedback, we did sensitivity analysis for all of the parameters of a point kinetic equation that could be changing in the reactor fuel cycle, for example. But I didn't include here because of the time. This curve here shows another way that we found to represent our instability boundary conditions now. It is not the instability plot, but we have the subcoolant number as defined before versus this void reactivity multiplier that was the parameter for each of these data. So in this this curve here, it is a simulated curve, while for conditions when we have the same few inertia and also for a constant fractions of decay neutrons here, you have only 2 data points for this term inertia. So you see these data points are very close, showing stability boundary in trace. So we can do that for several conditions. But again, we are not predicting the power, so we don't have the phase change number here. Since the average power is kept constant, we are actually predicting what is this void multiplier that leads to the instability condition. So it's a little bit different than it was very different than the data that I showed before, only without the neutronic feedback. The general results are shown here. There was one more analysis that was done by my PhD student, was to use the deep neural network as a machine learning model to also try to predict this data, which shows here in pink. But since we only have a very small range of subpolar number phase change number, you see that the machine learning predicts well close to the data, but everything else is extrapolated, so the shape it is not physical, since this was a data-driven model. But you see the general prediction here of the trace with an RMSE of 5% and SAHA about 9.6%. 𝗕liche was the most conservative model for these type of instabilities. Y-trace was the last conservative, but it was also the one that predicted better in this lower subipolar number. Just as the last slide for conclusions, these are the results of the first 2 years of the project. A few conclusions that we had, we proposed this phase shift methodology to define the instability and having a more consistent comparison among experimental investigation. We identified the minimum film boiling temperature as the most important role for the most important phenomena for this fail to rewet, but the heat transfer modeling that are going to add some physical model to the transition boiling, it is still an ongoing process. And also because we have done trace simulations to mimic the experimental data, the next year of the project, we're going to be doing trace park simulations to now try to translate how this data can actually be used for actual boiling water reactors. And also it's part of our work to do scaling analysis for boiling water reactors and define other non-dimensional numbers that can actually be useful for us to understand these instabilities. With that, I'm happy to answer any question.
Thank you, Juliana. That was a very interesting talk. We have some more time for questions. I see Saeed, you have your hand up. Please go ahead.
Hey, Juliana, thanks for this very interesting research that you're doing. I have a couple of questions. Number one is about the thermocouples. You didn't mention where these thermocouples are installed. Are they at the end of basically top of the core on each one of these rods, and you're averaging those, or where are they?
No, they are installed in not all of these rods that are in gray here. They are instrumented, and they are located in a few positions. The number of thermocouples is not proprietary. The location of the thermocouples are proprietary, but we have like 5, 6 thermocouples in each of these gray rods along the axial location where you'd expect to observe discrete heat flux.
Okay, so towards the maybe top where you expect the critical heat flux happens, is it how it's done or averaged? there?
It is not average. We do not average then. When the only average that was done when we calculated the heat transfer coefficient, because we only have one thermocouple, let's say in 15 centimeters of the rod, we have like one measurement. Then we have to average the heat transfer coefficient over that wall surface in order to calculate the heat transfer coefficient in that location.
Okay, the other question is that based on all the data I saw, basically the quality, exit quality, is it right that is about maybe 50% range, most of them 50, 60%, is that right?
Yes, it's very, very high quality and very high void fraction. I'd have to go back to my tables to give a number, but it's high quality.
So in the what's the flow regime there? I mean, if you have it in small channels, we typically obviously see definitely annular, but you have obviously very large channels. But in the schematic that you showed, you always showed towards the end bubbly flow. What's the flow regime there?
It's annular flow to dispersed flow. It's very high void fraction.
Okay, all right. So but the schematic that you showed did not show that actually we go there.
Which schematic?
There was one that showed region 1 and region 2.
Early on?
No, later. Oh, here, go
Here?
up. Yeah, right. So therefore,
yes, thank you for catching that. Yes, this it is from 𝗂𝗲 publication. So it is just to exemplify the difference between 𝗕ឆ and 𝗂𝗲. But when we did the drift flux model, we used the annular flow to calculate the void fraction. So we also modified a little bit their models.
So the dryout mechanism essentially basically evaporating films, just like we have in annular flow. That's what it is, right? Therefore.
Yes, it's film boil and dry out. Yes.
All right. Thank you.
Thank you.
Samir, can I ask you a question?
Please go ahead.
So Juliana, first of all, thank you very much. Super cool work. What I take home is that in many instances, you have a kind of a periodic boiling crisis going on, right? And then, you have a moment where this thing becomes irreversible. But isn't this periodic dry out a concern as well? Because you have, a certain frequency, and so isn't the cladding in those conditions subject to thermal fatigue and oxidation as well?
Yes, I would say. So we are doing a more approach that is like try to understand the phenomena. When we're talking with 𝗏𝗏 about these before the actually grant started. They were looking for the failure to rewet. They were most concerned about understanding the point where this temperature is not recovered anymore, right? For our flow instability analysis, if you wanted to be conserved, at the moment that we have this instability growing, independently if you're having these cycles or not, this is the moment that it's not safe anymore, because you can have a mass flow oscillation that will potentially lead to the onset of these oscillations. Now, in terms of if the cladding, you handle these temperature oscillations, you'd have to have more experimental data, as people are doing nowadays for accident tolerant fields, right? That they would be able to handle higher temperature for a longer period of time. That would be a point that in my opinion, we need more experimental data to actually see if this cladding can handle this, because these oscillations can go for a few hundred seconds. And then we need the more experimental data just to see if the cladding can sustain this without damaging.
These are all done with 𝗕𝗏, I suppose.
These were all done with zircaloy.
Thank you.
Or,
Yep.
yeah, yes.
Given that this is very frequent, like 2 seconds, it's very impressive. Does that cause a sort of fatigue because of expansion? Let's say you have constantly 50-degree up and down fluctuation. How does that impact? I mean, does it really translate to any appreciable, basically expansion and contraction, or no, it's not, just doesn't do anything negative?
So I think that's a follow-up question for Matthew's question. And my answer is similar. Although one thing that I can tell you, it is that these experiments were done with the same rod bundle, and we didn't see any change from for the first experiment to the last one. So the clad remains the same in terms of the measurements, you know. And now, if they did, I don't think they did a post analysis of the cladding after this experiment. That was not part of the project.
That's exactly what I was going to ask you. I would be very interested in a post analysis, right? Because we have seen these V-shaped marks on the rods as oxidation. I'd be very curious to see if you have anything like that. So
yeah, they have not looked to the rods after, but yeah, if we've done the experimental accreted flux before, there's probably that are oxidation, but not enough for us to see some change between the experimental runs. If you do analysis like over time, we didn't see any impact on that.
John, you have a question?
Yeah, I have just a kind of a simple-minded question. So you have these rods. Is it an actual reactor that you're doing the experiments?
No, these rods were electrical rods. We're basically applying current and voltage in the cladding of these rods to heat up.
Okay, so how do the power loads that you for the MIMIC experiment compare to an actual reactor?
Oh, sorry, I guess I went too fast and that point. So we control the power of the rods, basically controlling the current and the voltage. So the experiment had a reactor simulator, like they're called Sinan, that simulates the void fraction due to with the mass flow measurements. They simulate the void fractions, and they use this void fraction in the reactor model online to change the total bundle power. So it is the total bundle power that is changing during this experiment. That makes sense for you.
And so the 10 megawatt or whatever, how does that compare to an actual reactor for 20 megawatt?
Oh, we don't have so one thing that you might notice in these plots, I don't have any total power plotted, because the total power is proprietary. But the local heat fluxes are compared to the actual reactor.
Thank you. Cool.
Thank you.
I believe, Adia, you have any question?
I just have one question. Thank you
Yeah,
for the
sure.
great talk, Mr. Duarte. I was wondering if you studied how the surface characteristics of the fuel rod cladding would affect the rewetting.
Not in this project. Not
Yeah,
in
but
this
that's
project.
something
Yes.
that would be applied to experimental studies as well, to see like how the surface of the fuel cladding would affect rewetting and help in probably reducing the fuel at temperature.
I would say yes. We have a few researchers here, including myself, that work in this area.
Okay.
And the surface, we have seen the surface affecting the rewetting of these rods. It's a lower pressures.
Okay.
While when we go to these higher operational pressures, it seems that this effect becomes less prominent.
Okay.
But we don't have a lot of data at high pressures still available. There are a few works done by MIT and here ATWS at higher pressures that are starting showing these effects.
Okay. Thank you very much.
But one thing, if I can add, it is that all of these transition body and post-critical heat flux models that we have nowadays, they still have a very large uncertainty, and we still don't include effects of surface on those
Yeah.
models.
Exactly. Okay, thank you.
Okay, any other questions from anyone? Okay, if not, we can thank our speaker. Thank you, Juliana. Thank you for your very exciting talk.
Thank you again.
Thank you, Juliana.
Thank you.